Okay, good afternoon, everybody. My name is Mark Stewart. I'm the director of RSK's Geosciences business, and welcome to the July edition of our 2025 series of Down to Earth webinars. These cover a broad range of subjects, and all of which are available on our RSK's YouTube channel. So our talk today will be given by Dr. Charlotte Usher from our Geophysics team, who will be providing a guide to sustainable geophysics uses within the renewable sector. Firstly, we'll have a brief note on housekeeping during the talk. So all your microphones are automatically muted throughout the webinar, so we can't hear you. Hopefully you can hear us. During the presentation, you can post your questions online, and we'll have a Q&A session at the end. We'll answer as many of your questions as we can. If we can't answer any of these due to the time constraints, then we'll get back to you after the webinar. Shortly after the webinar, you should receive a link to a short survey. If you take a few minutes to provide us with some feedback, please, it'd be much appreciated, so we can improve these future webinars and provide subjects you'd be interested in. So now, please let me introduce our speaker today. Charlotte is a chartered geologist and a principal geophysicist, and she joined RSK Geosciences following her PhD and has been part of the team for nearly 10 years. So she is also our technical lead for geophysics, and she's actively involved in research and development, as well as working on large-scale commercial projects for a wide variety of clients. In addition, Charlotte was the lead author of the new Syria Guidance C812, and she aims to make the communication of geophysics more accessible and to increase engagement and the use as an alternative to or help to target intrusive investigations. So I'll hand over to Charlotte now. She can give us her guide to sustainable geophysics.
Thanks, Mark. Okay. So I'm just going to give a brief introduction as to what I'm going to be talking about today. So I'll start off by talking about sustainable ground investigation. So discussing what we mean by sustainable development and how geophysics can be used to help improve the sustainability of your ground investigation. I'm then going to go over a few ways we can use geophysics specifically within the renewable sector, and also a couple of other ways we can use it to help protect our environment and the ecosystem, and hopefully save a few coins in the process. And then I'll finish off with a quick summary before we have time for a few questions at the end, as Mark mentioned. So on to discussing sustainable ground investigations. So sustainability, or sustainable development, it's defined by the UN as development that meets the needs of the present without compromising the ability of future generations to meet their own needs. They've defined these 17 sustainability goals, which are just here. And these are what we need to aim to achieve to create a truly sustainable society. So it looks to find that balance between environmental protection, social equity, and economic development. So in other words, we need to be careful about how we use the world's resources. Within our business in geosciences, we have our own tailored goals to try and meet these targets. These can include things as simple as just raising awareness of sustainability within the business and outside, and getting people to think about it within their day-to-day activities. It's doing things like measuring our carbon footprint, thinking of ways we can improve the sustainability of our projects through things like reusing waste where possible, as well as integrating climate risk and resilience. So that involves us thinking ahead, looking at the bigger picture of the impact of our work, and not just looking at the particular job we're working on at a time. So when we're thinking of this in terms of a ground investigation, we have to think of it in terms of how this is going to add to the society, add to the economy, add to the environment. We want to measure the carbon footprint of our site activity. We need to look at what we're doing that currently results in any carbon loss or emissions. There's plenty of methods that we can use to reduce our environmental impact on an area. So we use things like good silt management and, as I said earlier, reuse of waste. But if I look at this as more of a assessment of a particular site activity, let's look at the impact of rotary drilling, for example. We might not do rotary drilling on every site, but in general, intrusive investigations will be part of pretty much every ground investigation. While the borehole itself shouldn't directly release a significant amount of carbon, the process to actually drill the hole is going to add to the carbon emissions for the project. There's various factors that are going to contribute towards this, which will include energy consumption. So the drill rigs and any associated equipment will generally require some form of energy for operation, and this is usually provided through the burning of fossil fuels. There's the potential release of subsurface gases. So this depends on the geological formation that you're drilling through. Some of them, or the materials that you're drilling through, will contain methane or other gases that can be released during drilling. This is dependent, as I say, on the specific geology, the depth of the borehole, and will generally vary between boreholes even on the same site, as well as site to site. So it's not a guarantee. Then you've got material transport. So any material that will go into a borehole, if it's being backfilled or if it's being lined to maintain use of the structure, the water that's used during drilling as the drilling fluid, or even cores that then come back to the lab for assessment. All of this material has to be moved around, and that will obviously have its own contribution to carbon emissions, which can be a particular problem if the site is remote or hard to access. And if we're really going to nitpick here, having a long-term presence of a borehole on a site could potentially create a pathway for pollutants to enter the groundwater, though you could argue in the majority of these cases, if the pollutants are already there, they're probably already in the groundwater. It tends to be why we're there to investigate in the first place. In addition, the casing or any backfill used within the borehole, as well as the production of the water used on site, those materials themselves, the creation of them will have their own carbon footprints. So as you can see, once you get into it, this carbon footprint thing, it's a bit of a can of worms to try and calculate the true carbon impact of the site. So for this particular example, I'm going to simplify it down a bit, try and make it a bit clearer. So the majority of site activities, no matter what you're doing, they're going to need to have somebody, usually with some sort of instrumentation, to physically go to a site, and that will be the same for everything. So I'm going to get rid of the carbon footprint of the actual equipment used, getting it to site. That's something we're not going to get rid of no matter what technique we're using. The same with the on-site material, like getting the equipment itself, the impact of that. Similarly, the creation of a possible pollutant pathway will hopefully be unlikely, particularly when it's been installed appropriately. So I'm going to get rid of that too. And it means that we're just left with the actual energy that's being consumed by the equipment and the possible release of subsurface gases or removal of carbon-rich materials that comes with actually drilling or digging into the ground. To put this into perspective with some numbers, sort of back of the envelope style, a study was undertaken by Atkins and Anglian Water back in 2022. This calculated the amount of carbon emissions from borehole drilling with a cable percussion rig or from trial pitting. So this is based off a standard site investigation where you're drilling 10 boreholes and 10 trial pits, with the drilling undertaken by a 15 kilowatt cable percussion rig. So if we need to drill more holes, dig more trial pits, go deeper, or go through difficult strata, for example, or use a bigger drilling rig, these values are going to go up. Now, if we compare this to a geophysical survey, these tend to be completed on foot. They tend to be fueled by battery power, which are rechargeable batteries. They're going to be relatively carbon neutral. The only carbon footprints generally from this, in addition to going to site, will be from food consumed by the engineer operating the device, which is fairly negligible in comparison. So you might consider this a bit of a claim, but let's look at this from another perspective. let's look at this site as an example. We know what used to be there. We know that it has been at least flattened to ground level. The standard approach would be to maybe drill a few holes, dig a few trial pits. We could do this in random positions. Maybe we put in a few more intrusive samples just to fill in some gaps. And maybe a few more. And we can keep doing that until we have a nice regular grid that's covering the entire site. So now we know everything, right? Except we don't. All of this area in red, this is the ground we don't have information on. So what if there's a feature here? Or here? We're not going to see that. And we've just spent a lot of money on those intrusive samples, running those drill rigs or the excavators for weeks and weeks to get all those samples. We've burned off a lot of fuel. We've removed loads of waste, which we potentially had to transport off the site, along with material to then backfill the holes, which we've transported on the site. And that's before we consider any risks that then remain in the ground. So now consider, as an alternative, we go back in time. We didn't drill all those holes. We rang our SK Geophysics team for some advice. And instead, they came to site and performed a quick on-foot reconnaissance survey with electromagnetic mapping. So this is completed using kit that is either hand-carried, can be towed, across a site with an integrated GPS to record the location. We can rapidly map changes in the conductivity across a site, and we can use those to then detect positions of things like building foundations, contamination plumes, buried utilities, and it's completely non-intrusive. So it doesn't break the ground, which reduces any exposure risk if there's any possible contaminants in the ground, for example. So from that, we can produce a map like this. So we now have data coverage across the entire site rather than in discrete positions. We can map out conductivity changes across the top 6 meters or so. And we can see that rather than finding a site where the foundations have supposedly been removed, these red areas over here suggests they certainly haven't. So that means we can now target our intrusive investigation. So rather than drilling 55 holes, several of which would probably have been unsuccessful due to the foundations that are still there, we can instead just sample, say, these 7 areas of the ground to try and figure out what the cause of the features are that have been shown within the electromagnetic mapping data. And that would mean that the drill rig or the excavators would only need to be on the site for a week or two, depending on how deep they're going. And that's compared to potentially months of work. It's a lot less time on site, a lot less fumes that have been released by the plant, and a lot less material removed. So overall, a much smaller carbon footprint to produce potentially a much more robust model of a site. Geophysics is a range of tools. I've said this before in previous down-to-earth talks. They provide information on material properties and they identify changes in the subsurface. Many of these tools don't break the ground at all. They can be hand carried or they can be pushed across a site. Some techniques can be rapidly deployed to map a site across the surface. Others can produce a 2D cross-section, sampling the ground across a range of depths below a surface profile. And there's also surveys that we can undertake from boreholes. Now, while intrusive surveys in the dark blue here, they'll tell you everything about that particular discrete location. But geophysics surveys will tell you at least one thing about this whole area or this whole area, which can then be used to interpret changes across the site validated by the intrusive investigations. Now I'm going to look I'm going to show you a few ways in which we can use geophysics effectively and sustainably within the renewable sector and for environmental protection. So first, I'm looking at solar farms. The application will depend on what the ground investigation is looking for. So as a few examples, we can use magnetic mapping surveys, and we can use these to find areas of increased ferrous material. So this could be in pursuit of unexploded ordnance, metallic surfaces, or even archaeological remains. Most magnetometers, like the one shown in the image on the top right, they're either hand carried or pushed on a car, or can be towed behind a vehicle around site. They don't break the ground. They are above the level of the surface. We can also, in a similar method, use electromagnetic mapping. So much like the example I showed earlier, or this example down below, we can use this to identify buried obstructions, shallow geological features, and metallic surfaces. This and the magnetic mapping surveys, they're collected continuously. The measurement positions are identified by the integrated GPS that's carried behind the user. And as I mentioned before, they're either hand carried or towed behind a vehicle. They tend to be used for rapid reconnaissance mapping for the shallow subsurface, and we can cover generally between 1 and 5 hectares a day, depending on whether or not the equipment is hand carried or towed. We can also use thermal resistivity probing. As you can see, this technique does require a hand auger. So unlike some of the other techniques, there is some material loss with this method. However, it's only a 70 mil diameter hole that's then augered by hand to specific depths. And then a calibrated probe can then be inserted into the base of that hole to collect a measurement, or several measurements at several depths, for example. And these are needed to calculate how much heat might be lost during any electrical transfer. There are existing standards that discuss these sort of tests. Another common test that is performed at solar sites is the vertical electrical soundings. These test the resistivity of the ground at a given point. Often they're used for things like earthing cables or along a proposed electrical cable route. And depending on how far apart your survey locations are, or the depth you're looking to survey, or even just the space you've got to survey, we can generally complete around 5 of these locations a day, but as I said, that can vary. If the engineers don't invert the data, you'll receive a 1D plot, like the one on the left here, of the apparent resistivity. So that's a bulk measurement of the ground from the surface to the measurement depth, alongside a table of measured numbers. But if you want more information on the ground structure, we can combine the vertical electrical sounding data with the intrusive borehole data or trial pits to model a best fit of what we think the resistivity would be for each ground layer based off what we're measured. This is a process called inversion. We can then use that to categorize the subsurface material and the resistivities across a site. Finally, we've got service avoidance surveys. So we would always advise that it's safe practice to have a competent person, like one of our safe ground team, to undertake one of these at every point you're going to be breaking ground. We generally use non-intrusive ground penetrating radar and electromagnetic locating surveys, as you would in a PAS 128 survey, but within a smaller area. So for example, 5 by 5 meters for a borehole location, or 7 by 7 meters for a trial pit. The resulting zone where no surfaces have been detected is marked on the ground and surveyed with a high precision RTK GPS system, and you get drawings for each location. The approaches for wind farms can be pretty similar. However, the infrastructure for a wind farm are obviously significantly different to those for a solar farm. So there's usually additional considerations we need to make during a ground investigation. Turbine structures are obviously very large. Onshore turbine blades can be around 50 meters in length on average. So not only do we need to consider how long that is, but also how that's going to move about the site, what the turning circle is. Do we need to consider the approach angle and the departure angle as we transport these over undulating ground into position? For this, we need to have obviously a good understanding of the topography of the site, the existing ground elevation, as well as what's going on below. We may have to smooth out the route to the turbine position to help get the infrastructure into position. So what do we need to add or remove to do this? We also need to consider that, as well as being large, they tend to be very heavy structures. So even once we've got the blades and the rest of the structure into the right position, the last thing we want is for anything to cause them to fall over. I mean, they've already got a bad enough reputation as it is. People don't want them in their backyards. They're considered an eyesore, so we don't want to add to that. For the most efficient design of a wind farm, we therefore need to know both the topography of the land, so how that surface changes, and what's going on underneath the surface. So your stratigraphy, your thickness of your soft sediments, the depth to the bedrock, how stiff the ground is, are there any voids? All of these geotechnical aspects to ensure that each turbine location is feasible. So to achieve this, firstly, we can look at doing electrical resistivity surveys. These are used to measure depth to bedrock, changes in stratigraphy with depth along a profile line. So these are normally completed in a cross shape at the base of the turbine itself, but can be used at any relevant position across the site. Similarly, we have seismic surveys, so we can do seismic refraction or surface wave surveys. These can be used to assess, again, depth to bedrock or how stiff the ground is, respectively. These can be acquired, again, in a cross-section at the base of a turbine or wherever it's required on a site to categorize the ground. We can also work out the elastic moduli for geotechnical assessment from these surveys. Similarly, borehole surveys, we can use these where boreholes have already been established and grouted into place to again calculate things like the elastic moduli in more detail, but within a discrete position with depth. Next, we have microgravity surveys. So these are a well-established technique for the assessment of voiding on site. You map the relative gravity changes across the site from a series of measurement positions. The relatively low gravity values indicate areas of lower density material, and these can be associated with things like voiding. The detectability of features from this technique will depend on how big they are, how deep they are, and how far apart the points are. They are generally used for things like the detection of mine shafts, which we obviously do not want under our turbine pad. But because they're quite a time-consuming survey, they tend to be used as a second phase activity. So they'll follow on from a reconnaissance survey, for example, with geophysics mapping techniques to then target the surveys to specific locations. Following on from this, it's related to wind turbines still, but there are points where establishment of structures such as wind farms or even other infrastructure requires removal of materials such as peat, which is obviously a high carbon storage material, particularly in areas such as the Scottish Highlands. Where there is a significant enough contrast, such as peat over bedrock, it is really easy to use geophysical surveys to map the depth of the peat. And we can use that to then help minimize the removal of the peat through efficient survey design, site design. And that also means we've then got less carbon loss associated with removal of that peat. It's a significant factor that has to be considered in wind farm design, both for the base of the actual turbine structure and the pad, as well as the roads that need to be created leading to each pad to get the actual infrastructure into place. And we have to consider all of this when we're assessing the environmental impact. Another thing we need to consider as well is things like animal burrows or tree roots. We don't want to build on or around or even undertake repairs that will potentially damage or disturb the existing ecosystem and its inhabitants. So it's an important assessment in infrastructure as well, such as flood embankments and levees. These are man-made. It's nice, soft materials, easy for creatures like badgers to burrow into, and it can obviously damage the structure. So in these cases, we want to be able to assess the position of things like burrows or tree roots, assess what damage they might be doing, where the burrows might be active, and we can then use that to better quantify any remediation or avoid repair or building activities that may disturb the wildlife in the ecosystem. Similarly, on the remediation side of things, as our need for land continues to rise, places where we've previously buried waste are being reclaimed. In some cases, the waste that is buried may need to be excavated, depending on the age of the landfill and what waste material is present. The example that's shown on this screen here is one of those cases. The client wanted to understand how much waste was present for the remediation of the site. We used geophysical surveys to successfully map the extents of the landfill using electromagnetic mapping, and those were able to be mapped to within 1 meter of the edge of the waste material. Cross-sectional geophysics was slightly less successful in determining the full basal extent of the waste, as the resistivity of the waste material was too similar to the underlying material. So a combination of the geophysics and the intrusive investigation was used to quantify the volume of waste, and this was quantified to within 0.3% of the total volume that was actually excavated. So in addition, the client was actually able to treat and reuse around 90% of the ground material present. So this accurate volume calculation from the ground investigation allowed for a far better assessment of the remediation costs than the client would have otherwise had. My final example is another example of finding the position of a feature using geophysics. In this case, it's a river channel. The channel had previously been moved upslope as part of a mill run, but due to the fact that it was above the natural groundwater level, it was prone to drying out, particularly in the summer. So they wanted to re-establish the channel back into its original position. The old floodplains were mapped out using surface geophysics techniques, which included ground penetrating radar, as well as electromagnetic mapping. And then they were also validated, the results from these were validated with cross-sectional electrical resistivity surveys, and then also targeted borehole surveys. As you can see, the channel structure was able to be mapped reasonably well, as the material of the channel was gravel which was very different to the clay alluvial deposits that were surrounding it. And this survey all led to the successful re-establishment of the channel in its natural position. So, just to summarize, the geophysical survey and type of survey and the method that you end up using, or perhaps not using, on a site will depend on the site itself and on the scope of the investigation. And they will often be used alongside intrusive investigations. Surveys will not be guaranteed to work the same way on two different sites, even if they have the same scope, the same aims and objectives. Ultimately, though, where you can use geophysics, you will have many benefits, including you've got a much larger amount of data covering more of the site, which you can use to produce a much more robust model. Many of the surveys potentially don't break the ground at all. They use minimal energy and additional materials. You will reduce the overall environmental impact compared to just using a standard intrusive investigation. You have ways that you can use it to help protect the ecosystem and the creatures that live there. And overall, because use of geophysics allows us to target an intrusive investigation, we've therefore got an overall reduced carbon footprint of that ground investigation. Thanks for listening. It's time for any questions.
Thank you, Charlotte. That was really good. A great reminder of geophysical techniques we can offer and how certainly how they can complement intrusive investigations to provide a more sustainable investigation. So that's really good. Thank you. We've got a couple of questions here that have come in. Just have time. If you've got any burning questions, please drop them in the chat and we can look at them now. So the first one, are there any cross-sectional methods that don't break the ground surface, so that, for example, pollutants don't get introduced into the groundwater?
Yeah, so a fair few of the cross-sectional stuff that we use, such as seismics or electrical resistivity, they do have spikes that go into the ground. Unfortunately, there aren't any alternatives for electrical resistivity methods. So if we're looking to completely not break the ground surface, we'd have to discount those from that sort of situation. But we can still use seismic surveys because we have technology which allows us to do that from the surface with land streamers or tripod geophones, which unlike the traditional spiked geophones, they don't break the ground. We also have obviously a lot of surface mapping techniques. A lot of the equipment we have now lets us measure at a range of depths. So they will be allowed to give some sort of like cross-section information. And we've got things like GPR as well. I always like to say it's a really versatile technique. Depending on what equipment you're using, you can do 1D, 2D, 3D, even 4D collection. You've got great resolution potentially. You have got potential drawbacks with, if you want more depth, you lose your resolution, and certain ground types like clay aren't so good. But in general, all of those, there's loads of different choices of things we can use from the surface that don't have to break the ground any more than treading on it, for example.
Okay, great. Yeah, we've got some more questions coming in now. So the next one, how energy efficient are geophysical tools and methods, and are there any efforts to make these geophysical surveys more eco-friendly?
So it's quite difficult to fully quantify the actual energy efficiency of the actual tools themselves. Obviously, I don't know a lot of details about how they're actually made, but in general, compared to say more traditional methods, they are pretty energy efficient. As I mentioned in the talk, a lot of our kit runs off batteries. These tend to be rechargeable batteries, obviously, that reduces waste. All of our equipment's hand carried. While it's not always easy, some of it's a bit heavy, but generally where you can walk by foot, you can get the equipment there. So we're not going to increase emissions from transport in that sense. We don't increase noise pollution as well, because a lot of, obviously, if it's being carried by foot, it's not loud, like not compared to a drill anyway. Generally, we try and replace equipment, not replace, sorry, we're trying to repair equipment rather than replace it, which it's non-disposable, which again reduces waste. There's some equipment even that uses passive energy, so we don't even have to create a source. So the only energy that's going into it is like just powering the receiver, and a lot of those run off like even solar chargers if they're left out for monitoring. Yeah. So, and obviously not penetrating the ground reduces waste loss as well. So.
Okay. Well, airborne geophysical surveys, can they be conducted for environmental studies?
Yes. So, obviously, historically, helicopters would traditionally have been used for those sort of airborne surveys, and the equipment that's used on those, again, traditionally tended to have been more for like mining surveys, because the actual output is coarser, and therefore for the sort of detail we need for environmental surveys, it's not quite the resolution we need. But technology is now being developed to be able to fly those surveys off drones, which are obviously a lot smaller. You can fly them a lot closer to the surface, so we can get a lot more detail, which is then making them more applicable to use for environmental surveys. And I can only see that increasing, and the amount of us being able to use those sort of surveys increasing with time.
And a lot cheaper.
Hopefully.
One about our carbon footprint again. Should we also include emissions relating to computing and storage for data processing? Have we quantified this anywhere?
Very good point. Yes. So obviously, no matter what the survey, we're going to have some sort of output, whether that is seismic data or even a geological log from the actual window sample or whatever you're doing on site. Granted, the actual computing power for a geophysics survey is going to be higher, but with a lot of that actually being on cloud-based processors now, especially as data is getting larger, the actual cost of that is going down in a sense, because it's being done on the cloud rather than on in-house servers. So
okay, maybe that's something.
But it is, yeah.
Okay, well, that's all the questions that we have in today. So thanks, Charlotte. So I'll bring it to a close. Our next Down to Earth talk will be Tuesday, the 9th of September. So please look out for that in your inboxes. Please, if you can, remember to complete the survey that you should get a link to shortly. And thank you for attending today, and we'll see you all again, hopefully in September. Have a good summer.